Our next speaker is Dr. Stavros Vougioukas. He works in the Department of Agricultural Engineering here. He has worked primarily in strawberry and pear harvesting. And with him, you're going to get to see what I really want to see in our harvesting is robotic harvesting, because as I was expressing to Kyle earlier, what I really want to see is all these little machines running around in the orchard all by themselves, and somebody back at their computer or out there with a joystick watching, but running the machines around as separate units. Because what I very firmly believe we need for mechanical harvesting is smaller machines that are robotically controlled and have separate units. So if one thing goes down, the whole show doesn't go down. And with that, I'm going to introduce Dr. Stavros Vougioukas, who's going to talk to us about the theory and research in mechanized and robotic harvesting. Stavros?
Well, good morning, everybody, and thank you for the invitation to present to you today. Luis, thank you very much for the introduction and for a very interesting presentation on mass harvesting. The topic for my presentation is theory and research in mechanized and robotic harvesting, and so don't worry, it's not going to be a lot of research. There's not going to be a lot of theory, no equations, and no quizzes afterwards. What I would like to discuss in this presentation is some issues related to robotic harvesting that are not really technology specific, but I would like to give some insight as to why robotic harvesting is difficult and what could be done to improve the situation, accelerate innovation in that space. So just as a brief introduction, I work in the biological and agricultural engineering department. I run the bioautomation lab, and we run a gamut of activities. We are very active in collaborative robotic harvest aids, and also in mechanical and robotic food harvesting. But we also have a lot of activities in general autonomous operations in orchards, projects in precision yield mapping for manually harvested crops like strawberries or nuts like almond, pistachio. And then we also do some projects in post-harvest automation. But the focus of today's presentation is on harvesting. And so, I don't need to explain this to this audience. All fresh market fruit and vegetables are hand harvested. And, these are frail products that must be harvested with near zero damage, and also very often selectively. Sometimes that's not necessary, but typically we need to harvest in multiple passes. So what are the three major mechanization approaches? Well, they are listed here. One is harvest assist. So these are technologies that make it easier, faster, safer for people to harvest. They increase efficiency. The second approach is mechanical mass harvesting, and Louise did a great job presenting some of those approaches and challenges for olives. And then the other approach is robotic selective harvesting. Okay, you see the difference here between mass and selective harvesting. Robotic is always selective. Mechanical is typically mass harvesting. Now, in terms of harvest assist machines, they've been around since the 40s and 50s. And you can see, these are black and white pictures. You can tell from the clothes of the workers, these are old. The picture on the left is actually from 1967, and the one on the right is from, again, the late 50s or 60s. The idea here is that pickers spend a lot of time either climbing on ladders, relocating ladders, walking to the bin to unload the fruit. So introduce orchard platforms. That's the machine on the left. And then on the right, you have essentially a large conveyor belt that's moving at crawling speed. And the people who harvest either strawberries or vegetables, instead of walking long distances to deliver their harvested crop, they walk behind the machine and they deposit the harvested crop on that machine. I call this the early days because this is what those harvest days looked like. Nowadays, in many cases, they don't look very different. So this is, just one modern orchard platform on the left. There is not much difference between these and platforms 50 years ago. Um, However, there has been innovation in this space. This is an example of a platform where it uses vacuum tubes so that it makes it a little bit faster and easier for the pickers to um, put their fruit, their harvested fruit, into a receptacle, and then the vacuum takes care of conveying, transporting the fruit from the picker to the bin. Since we are discussing harvest aid machines of the present or the future, this is something that we developed locally in Davis. This is a harvest aid robot, actually, that is used in strawberry harvesting, or at least at a pilot scale. The idea there is that instead of having a long, large conveyor where the pickers walk behind it, you have multiple robots, autonomous machines roaming around and transporting the trays for the pickers, thus saving anywhere from 10 to 20% of their time that they spend just walking back and forth and delivering trays. So this is, of course, a research prototype, but there are already at least one company offering simpler versions of these robots for table grapes, and a couple of other companies trying to enter this space for other crops. Now, in terms of mass harvesting, Luis already did a great job of explaining how that works. Practically, we have trunk or canopy shaking. With trunk or canopy shaking, we can achieve pretty efficient and fast fruit removal. It's not selective. The issue there when we try to harvest fresh market fruit is that there is considerable bruising. And so these approaches are not really used for fresh market fruit. Their use is limited on food that will be processed. For example, clink peaches, tart cherries, um, um, olives, like Louise explained. And these are some machines from the past. You can see these are, again, black and white pictures from the 60s. On the left is a canopy shaker with rods. I'm sorry. And then on the right is a trunk shaker that receives all of the fruits on a catching surface and then tries to convey them on bins. These are examples of machines nowadays. On the left here, I believe, Luis, this is an incarnation or a version of your machine. And then we see other canopy shaking machines, specially designed for small trees, and then trunk shaking machines, shake and catch type of machinery. So again, these are not really used for fresh market fruit. Now, what about robotic harvesting? We hear a lot about it, we read a lot about it in the news, lots of activity, lots of startups, lots of research groups working in this space. Uh, the truth of the matter is that robotic harvesting is not a new idea, okay? And the feasibility of it has already been established or shown since the 70s and 80s. I really love these old black and white pictures, maybe because I'm a old gray hair guy. And so on your left, you can see an example of a black and white camera imaging an artificial apple tree in the lab. You see here a robotic arm. This is from 1977. This was like a demonstration of finding fruits in a canopy and using an arm to pick them. This picture on the right is much more real world. And actually, our very own David Slaughter, he did this as part of his thesis at the University of Florida. You see here a large machine with a robotic arm. There is a camera, and then the camera is used to detect and localize citrus fruits, and then go and pick them with this robotic arm. So robotic harvesting has been around for more than 40 years. Okay, what about today? Well, we'll see what's happening today. This is a video from 2004, Tom Burks and Hanan from University of Florida. Again, autonomous harvesting, and you can see here a pretty large machine working pretty smoothly. It's dropping the fruit. It doesn't really, place them in a bin or something, but it's a research prototype demonstrating that it can be done, right? And if we go now to 2020 or 22, these are some examples of robotic harvesters now. And this is just a very small sample of existing machines. In the very center, this is a research prototype for bell peppers. You can see again a robot arm and a camera. And then bottom right, this is a robotic harvester for apples using a vacuum gripper. This used to be Abundant Robotics, startup here in the Bay Area. It closed down, opened up again. We'll see if that effort continues. And then something interesting, you can see top right and then top left, these are multi-arm harvesters. The one on the left is for kiwi fruit. The one on the right is for apples. And then bottom left here, our very own Davis Advanced Farm. This is a robotic machine for picking strawberries. There is another at least 7 to 8 startups working in robotic strawberry harvesting at this point in time. So lots of robots out there, but the truth of the matter is that most of these robotic harvesters are actually still prototypes. That means that you cannot really go out and buy any of those. And in most cases, you can't even ask the company to come and offer robotic picking as a service. Okay, and if that happens, it's a very limited extent. So what's the issue there? Why, although we've been working on robotic harvesting for at least 40 years, we got all this technology, cheap electronics, AI, machine learning. Why do we still struggle with robotic harvesting? Well, the bottom line is that building a cost-effective harvesting robot is very difficult. And there is a very important thing to consider, that harvesting cost is a very important factor. You can always build a machine to harvest fruit and publish a paper about it, but building a machine that actually harvests in the real world in a cost-effective manner is very difficult. We already know from economic studies that harvesting cost is defined by mainly 3 factors. Factor number 1, and this is this order, is the fruit picking efficiency. This is a percentage. If there are 100 fruits on that tree or in that block, if you can harvest successfully 90 of those 100 fruits, and when I mean harvest successfully, it means grab those fruits from the plant or tree and then safely put them in some container where the workers would put them, and they arrive in that container in a way that they're marketable, then you have 90% efficiency. Okay, so fruit picking efficiency is a percentage. The second factor, again in that order, is harvester purchase price. That's in dollars. Now, we are not going to talk a lot about this factor today because one of the interesting advancements or evolutions of robotic and automation technologies is that nowadays companies are offering automation as a service rather than selling the equipment. And so harvester purchase price may not be relevant if we want to consider robotic harvesting. Of course, it is relevant to the company that's building those machines because they need to charge, right? And then the third factor, which is extremely important also, is the pick cycle time. How many seconds does it take to pick one fruit sustainably? So I'm going to argue that fruit picking efficiency and pick cycle time, because they are so important, we need to pay a lot of attention to them, and they are not easy parameters to maximize. So let's look closer at the picking efficiency, which is of course a percentage, like I said. Imagine that you have a robotic harvester. I don't care about the technology or the gripper, if it's vacuum or if it's a mechanical gripper, or if you're using, computer vision or AI. We don't really care about the technology now. But imagine that you have this machine, and when you go to pick and you look at your plant, there is a percentage of fruit that is visible from your perception system. Okay, that means that if there is 100 fruits in that canopy, maybe 70 or 80 or 99% of those fruits are visible by your system. Now, out of that percentage, another percentage will be actually perceived by your image processing, computer vision, or signal processing system, and that's an extra percentage that we need to take into consideration. Out of the fruits that your system actually detected and localized, they were perceived, only a certain percentage will be reachable by your machine. Okay, it's not going to be always 100%. And then out of those fruits that are reachable, only a certain percentage will be successfully detached. By that I mean that some fruits will not be able to be detached and they will stay up there, or when you detach one fruit, another one will fall because of clustering, for example, or you will damage it. And so only a percentage of fruits are successfully detached in being marketable from the plant. And then out of those fruits, only a certain percentage will be successfully conveyed from the gripper to the bin or to the tray where they need to end up. Now, we see all these stages. The problem is that the overall efficiency of the system is the product of the individual efficiencies, if you will. And that is a big problem, because when you multiply numbers that are smaller than one, you come up with issues. Even if all of those numbers are high, let's say 95% efficiency, if you multiply them all, you end up with a 77% efficiency. That means that out of 100 fruits that were out there to be harvested and sold, only 77 are actually harvested by your machine. What is the typical efficiency of a human picker? It's more than 95%. These people are very skilled, and they can spot and grab more than 95% of the fruit on the tree or on the bush or wherever. And even one weak link in this chain will bring the entire product down. Now, where are we in terms of efficiency with current machines? Well, that's not an easy question to answer because, of course, no startup will disclose and support numbers out in the open because, if those numbers are low, then there's a problem. If these numbers are high, they will be questioned like, are they high always? Under what conditions was the testing done, etc. Let me give you an example from a harvesting robot in New Zealand. This is a pretty recent example from 2020. This is from a peer-reviewed publication. This robot is pretty cool. It's a collaboration between a university and the startup. Actually, the startup came out of a research group in the university. This is a 4-arm picking machine in New Zealand. So these are the numbers they reported, and not everybody reports these numbers again. Out of 100 kiwis, only 93 were visible, and that's not always the case. In some cases, they explained that that number was much smaller. In some cases, it was a little bit higher. But in the trials that they ran, and they harvested about 2,000 fruits, they got a 93% visibility. They also got a 98% perception rate, which means that all the machine learning and the image processing works really well. That was not the bottleneck. Out of the perceived fruit, only 43% were reachable by these arms. Now, these arms are not the first iteration. They underwent multiple iterations. But you see here that the big bottleneck is actually the mechanical components. It's the design of the arms. Then once that gripper made it to a kiwi, 87% were detached successfully. That's a pretty good number, but it's not 100%. Especially clustering creates issues. So you have kiwis being dropped or not being successfully picked. And then 95% of those kiwis were actually conveyed successfully without any bruises. Conveyance here happens through these tubes. So the kiwi is grabbed and then it falls through this tube and enters the system. However, you see that the overall efficiency here is 32%. So that's not a very high efficiency, and clearly this robot would not be successful commercially if it were deployed in its current state. I repeat here that there are not many results out there about existing robots. Only research groups in universities publish such results. I haven't seen any such results from industry. Now, how can we improve the picking efficiency of these machines? Well, if we look at the chain of harvesting and we consider visibility first, clearly something that we need to do, and Luis already talked about it for mass harvesting, is to introduce simpler canopies. So we want canopies that are more geometrical, if you will. Their geometries are such that the fruits are on the outer parts of the canopy. Perhaps they have less foliage. Maybe you have to de-leaf or breed something that has fewer leaves, although biologically that doesn't mean that it's plausible or it will give you the productivity that you want. And you also want less fruit clustering because when fruits hide behind other fruits, they're not visible. So that's on the plant side, but on the technology side, it would help if you have multiple cameras looking at your target from multiple viewing angles. That has been shown to increase visibility. You might have active viewing. That means cameras that actually move independently, or actuators, robotic arms, where the cameras are on the arm. And so as you pick something, you also get better view of the canopy that you are picking. Um, Other approaches are canopy actuation. So either compress the canopy, Crew Robotics is doing that for strawberries, leaf blowing with streams of air, that has been tried too. But as you can see, uh, uh, improvements here can come from the breeding or the cultivation or pruning side, horticultural side, and also from the technology side. Now, if you look into perception, we're already doing pretty well, but of course, better algorithms and more data will always help boost that percentage. But typically, that's not the bottleneck of the operation. What about reachability? Again, if you have canopies of smaller volume, more geometrical, more narrow, simpler, without too many branches that present obstacles for the arm going in, that will increase your reachability. And on the machine side, how do you design your machine, the entire machine and the arms, and also how you control their motions and plan their motions, that also will influence the reachability. In terms of detachment, clustering is a big issue. You want to avoid fruit clustering. That can be done through breeding, that can be done through fruit thinning or flower thinning or both. Um, and then on the mechanical side, again, you need to design your gripper in a way that successfully detaches fruit. It doesn't bruise them, and also does it in a way that doesn't harm the other fruits that are nearby. The control algorithms are also very important here, because in robotics, the mechanical side and the software side have to work together very, very well. Finally, conveyance. Well, it would be nice if we have fruits or crop in general that is resistant to damage. So, for example, tomato harvested from Davis, a tomato with a thicker skin. Perhaps we could have crops that are more resistant to scratches or bruises on the crop side, and then also on the robotic side, how do you design your arm and how do you design your machine? These are very important factors. Conveyance can be very, very important, and it's often neglected because, uh, as we will see, it also influences a lot, not only the efficiency, but the peak cycle. So, to summarize, fruit picking efficiency is a very important parameter that dictates harvest cost, and then we need to consider it very carefully. What about peak cycle time? Well, again, if you think of the motions, the actions that take place when we are harvesting, these are the following. The robotic system needs to position itself either in front of the tree or in front of the specific part of the canopy or the plant where the fruits are. It also needs some time to perceive, to detect and localize the fruits. It also needs some time to actually reach out there and get the gripper to touch or grasp the fruit. There is also some time needed to detach the fruit from the plant. And you also need time to transport that fruit from the gripper to the bin or to the clamshell, the tray, whatever that is. Now, all of these times need to be added together to come up with the seconds per fruit that you require. Well, is that difficult or easy? Well, again, it's not easy because when you add things, if something takes longer, it dominates. For example, you might have an amazing robotic system that's very fast, it can reach the fruits very quickly, but then if transportation of the fruit from the gripper to the bin takes a long time, your peak cycle time goes down the drain. It's too high. How are humans doing? We said that in terms of efficiency, humans can achieve more than 95%. Let me give you some examples. Manual strawberry picking in Salinas. It varies wildly, but somebody may take 2 to 5 seconds to manually harvest a strawberry. Now, that doesn't include the walking time back and forth to deliver the strawberries, but like I said, if you're using robotic transport systems, harvest aids, that time is almost zero. So this is something like a baseline, right? What about apples? If you put a person on an orchard platform so they don't need to climb ladders, we've measured that it takes about 1.5 to 2.5 seconds to harvest an apple. Mind you, these are our own measurements. These are not from literature, but literature agrees more or less with these numbers. Now, how about robots? How fast are they? Well, again, if you look into literature, there is very little data. And because most robots in literature are prototypes, you may see numbers that range anywhere from 6 to 10 seconds to half a minute. So those numbers really vary wildly. Let's go back to the Kiwi example, which is a startup that actually published data. Well, they reported 3.25 seconds per kiwi for a 4-arm harvester. I'm not familiar with how much time it takes for a human picker to pick a kiwi fruit. I suspect that it's less than that, but this is a pretty decent amount of time. If we go back to strawberries, how long it takes a robotic harvester to reach and pick one fruit. A recent paper doing an economic analysis assumed anywhere from 7 seconds to 19 seconds. But again, there is not much information there. Now, how can we improve the peak cycle time? Well, if we look into position, plant spacing and canopy volume are very important because, as you have denser plant spacing, it takes less time to go from one plant to another, but also as the volume of the plant or the tree becomes smaller, it becomes faster to place your arms closer to where you want them to be. Machine design and control algorithms are again of paramount importance to reduce the positioning time. In terms of perception, perception is not generally the bottleneck. Of course, faster algorithms, faster hardware can always help. But here we are talking about the speed of electrons rather than the speed of mechanical components. So in general, this is again not a bottleneck. Other things that have been tried are interleaving perception with action. So you don't really need to add the perception time to the rest of the links in this chain, but perception time may be part of positioning, for example. Reaching, that's very important. If you are close to the plant and the smaller and simpler the canopy is, the faster it's going to be for the arm to reach the fruit. Also, if there are no branches in front of it, that makes it much simpler and easier to go and grab that fruit at a greater speed. Machine design, how many degrees of freedom your arm has, how is the gripper designed, your control algorithms, your motion planning and avoidance algorithms, all of those affect the reaching time. Detachment, fruit clustering is very important here. If you have a lot of it, then you need to approach more carefully the fruit because you don't want to damage fruits next to it. So that is very important. And again, gripper design and controls. And then finally, in terms of transport, this is of paramount importance. How do you get your fruit from the gripper to the bin? Abundant Robotics, for example, was using vacuum tubes in order to convey the apples from the gripper to the bin. That's a great system, but it's very expensive, and but it's very fast. Also, it may not work for fruit that is non-spherical or has fuzz on it, like peaches, but it is a very fast approach. Other approaches are simply pick and place, grab the fruit and then waste some time of the gripper to transport it to a container. And there are some alternatives out there. So again, the ways to improve come from both or can come from both the breeding, the horticulture, the planting, but also from the technology side. And finally, these are not the only challenges. There are some other systems challenges that are also very important and haven't been paid attention to in the literature, but we don't really know if they have been paid attention to in the startup world. One is that if you want to increase throughput, you need to deploy multiple arms. One arm will not cut it, even if it's 1 foot per second, which, you know, it's not going to be 1 foot per second. So the bottom line is that deploying, let's say, 10 arms is not going to increase your speed by a factor of 10. It's not linear. The main reason is that the fruit density varies. So every arm working in a certain space doesn't have in front of it the same amount of fruit. And that can bring imbalances in the arm load. So if you have 10 arms and one of them is very busy and another one is almost idle, that effectively will mean that your overall throughput is going to be much lower. Okay, so this is an issue that hasn't received enough attention yet. So careful robot arm scheduling, programming when you have multiple arms is very important. The other component is the harvester travel speed. If you have a robotic harvester with 10 arms or 20 arms or 5 arms, how fast does that harvester move? If it moves very fast, then the efficiency suffers because the arms don't have enough time to pick all the fruit, and so you leave some of the fruit in the field. However, if you move too slowly, then maybe you get a very high fruit picking efficiency, but then your harvest speed suffers. So clearly there needs to be some sweet spot, some optimal speed that really depends on the fruit that you have in front of you and on the picking speeds of the arms. This is again something that affects a lot the efficiency and the speed, but it's not always trivial to address. So to summarize, these were the major challenges for robotic harvesting of any type, regardless of technology, embodiment, and crop. And I wanted to convey the message that things are looking good. There is a lot of activity. There is a lot of R&D in this space. But sometimes we hear that, oh, you know, the robots are here, everything will be harvested robotically, etc. That's not necessarily the case. Like Luis also said, if the market is small, It's very unlikely that you will see a robotic harvester specifically for that crop. We will first see robotic harvesters for strawberries, for apples, the big crops. Citrus is a big crop, but that's not an easy crop to robotically harvest. And then I will just conclude with a current project that we are pursuing in my lab, and it's trying to address some of those challenges. This is the peak cycle chain that I explained before. So this is a project in collaboration with Carnegie Mellon. They're looking on the perception side. We are doing the mechanical side. And so the idea there is to use multiple cameras to harvest apples or tree fruits in general, and then also use controlled airstreams to agitate the foliage so that you increase the visibility, but you also increase the speed of harvesting. And then we are developing a multi-arm machine that is low cost. It deploys multiple arms, but those arms are programmed in an optimal way so that they are perfectly or almost perfectly load balanced to achieve the highest peaking throughput that we can reach out of them. Take home message: when we hear agricultural robotics and agricultural robotic harvesting, um, what are agricultural robots? You know, in the field of robotics, on one side, we have field robotics. This is a well-established field. And when we talk about field robotics, we refer to machines, autonomous robots that operate in uncontrolled, uncertain, unstructured environments. And the key, the focus is on robustness and adaptability. Now, on the other side of the story, we have automation. We don't have field robotics. We have automation where you deploy machinery in a factory floor, for example, in a controlled, known, and structured environment. The focus there is on high throughput and repeatability. Well, guess what? The challenge with agricultural robots is that they lie in the intersection of two fields, field robotics and automation. So we need to build machines that do not operate in a factory floor. The environment is semi-structured, it's not fully structured, but we also want to be very fast and very repeatable. And so achieving that, working in that intersection of robotics, field robotics, and automation is very challenging. And with that, I would like to end my presentation and take any questions. Hopefully, I didn't exceed too much my allocated time.
Stavros, is it easier for you to access the questions via chat and address those questions here to the audience at this time?
I believe so. So I see a first question. Can you let us know which companies are already offering the robots to move strawberries boxes from the field? As far as I know, there is no company out there that offers robots as harvest aids for strawberries. There is one company called Burro, Burro. They offer small robots for table grape harvesting. But those robots are only operating in vineyards and not in strawberries. I see another question. Can you please comment on the potential for the robotic arms to cause damage to fruits that were unripe at the time of harvesting, not meant to be harvested at the same time? So yes, if the control is not perfect, and if the gripper design and the arm design are not perfect, it is always possible that the arm, in its effort to grasp a marketable ripe fruit, will actually cause damage to a nearby fruit, maybe a fruit in the same cluster, or maybe it will cause one or more fruits to drop. Actually, that happens with people too. If you see people harvesting apples on a platform or on a ladder, they try to move very fast to make more money, of course. And as they will pick a fruit, sometimes they will drop another one. Of course, often they will grab two fruits with their palm, or maybe use both hands to grab an entire cluster. But this happens also with humans. Also, damage to flowers, where in crops like apples, for example, there are no flowers there. But if you were to pick, I don't know, lemons, and there were flowers together with fruits, it would be possible to also damage the flowers as you're harvesting. Another question I see, the actual machine designs take into consideration external conditions, rain, mud, uneven ground. It depends on the machine. First of all, maybe they don't need to. For example, no machine may go out to harvest strawberries if it's raining. Also, it doesn't rain that often, right? In terms of mud and uneven ground, yes, they have to be able to traverse terrain that is not really extremely flat or even. Here in the valley, we have very flat ground, but also there are strawberry fields that are not on even ground. And it really depends on the product, on the robot, whether the company has invested effort into making it able to go uphill, or maybe they're just targeting flat terrain. The other question is, have you worked with ethafone or other chemicals in mechanical apple harvesting to increase stem abscission? Personally, no, I haven't. When it comes to robots, this is not such a huge issue because the gripper can exert a lot of force and pull out the apple, but also there are designs that actually have a blade and cut the stem. I'm not saying that an abscission chemical may not help with pulling apples or other fruits out of the canopy, but personally I haven't worked with it, and I'm not aware if others have. Most of the robotic harvesting research focuses on the design, the controls, rather than on making it easier to pull.
I think at this point, Stavros, we're going to have to ask you to see the other questions during the discussion section and move on to our next speaker. Thank you,
Great.
Stavros. That was excellent.
Thank you very much.